This is multivariable calculus, and in this video, I'm going to talk about section 16.2, line integrals. And when we talk about this, really what we're going through here is we're talking about the idea of integrating along a curve. So typically when we've been doing integration up until this point, we've been integrating along the x-axis, along the y-axis, along the z-axis, in a theta direction, in a phi direction, whatever it is. But we've typically just integrated in a direction. And now what we're going to do is we're going to integrate along a curve. So it's a little bit different from what we've been doing, but what it allows us to do is to start thinking about things that are moving along a curved path. So for example, when I'm calculating the amount of work that's going to be done when an object is moved, I'm no longer restricted to just moving in a linear direction. Now I can have an object that's moving along a curved path, and I can evaluate how much work is done when I move along that path. Okay, so let's talk about how a line integral works. Okay, so you can see here what we're doing is we're trying to think about how would we integrate instead of along the x-axis or the y-axis in this diagram. How would we integrate along this curve that we have here, this curve C? And if you notice here, we're going along these points from P0 to P1 to P2 and so on. And when I'm thinking about what we were doing before, when we would do a rectangular approximation, we'd have a linear base that we would be thinking about and doing a rectangular approximation in that way. So it's very different conceptually from the standpoint of I no longer have that linear piece as the base when I'm thinking about what I'm going to add up. So what we do now instead is we integrate along the curve, and we're going to have arc lengths as the distances that we're moving between the points. And in addition to that, to start with here, we're going to integrate with respect to our parameter. So we're going to integrate typically with respect to t. And when we do that, we're integrating with respect to arc length when we do the setup for this. So we're also going to end up integrating with respect to t when we integrate with respect to x or y in the end. But when we integrate with respect to arc length, we start by thinking of this as a piece of the length of the curve, and then it sort of converts over into an expression in terms of t. And you'll see what I mean as we go through some examples here. Okay, so this is the way that we are going to set these up. So if I'm going to do a line integral of a function along a curve, this is the notation that we're going to use. And what I want you to see here is this notation slightly different than what we had before. So you can see here, we're saying we have a curve C. And when I integrate along that curve C, notice that I have this ds here. That tells me that I'm integrating with respect to arc length. And that's important to note because when I set these up and when I interpret my results, it's slightly different if I integrate with respect to arc length or if I integrate with respect to x or y or z. Okay, so in the end though, what I'm doing is I'm taking my function times, instead of a delta x or a delta y or a delta z like we did before, we're doing a delta s. So a small piece of the length of the curve. Now remember, we talked about what delta s is back when we did arc length. And so really what we do is we substitute into our integral for ds, we substitute our arc length expression. And right now we're looking at this in 2 dimensions. So you can see that we've got our function in terms of x and y. Notice x and y are functions of t. And then now here's my arc length piece of that. That's what ds is equivalent to when I think of it in terms of the parameters. Okay, so let's take a look at actually solving one of these out. So the question says, using the given parameterization, evaluate the line integral along the curve C, 1 plus xy squared ds. Okay, so what we have over here, notice we have a vector function that's given, ti plus 2tj, and for the t values, we're going between 0 and 1. So our parameter is restricted between 0 and 1. Okay, so there's a couple of things that I'm going to need to do this. And a lot of times you can just do this as, a step in your head. But we know that x of t is equal to t. We know y of t is equal to 2t. So what that tells me is that if I want r prime or dx dt, dy dt, I'll write it as r prime that would just be equal to the vector 1, 2. Okay, so remember we need that because we've got to know that arc length expression. Okay, so let's talk about how we would write this out. So the one thing you're going to want to get used to is the idea of the notation that you're going to use. So I'm integrating along the curve C, and I'm integrating this function 1 plus xy squared ds. Now what I want to do is I want to convert that ds over, and I also want to convert my x and my y over into their parametric forms, because in the end, I'm going to get an integral in terms of t that I can solve. Okay, so now this integral is equivalent to 1 plus xy squared would be 1 plus t times 2t squared. And then when I do my square root of dx dt squared plus dy dt squared, I'm essentially going to get 1 squared plus 2 squared, which is 5. So all of this is going to be multiplied by the square root of 5. And then that's going to also have the differential dt. Now, my limits of integration here, I'm no longer just going to say just the general c. Since I've converted this over into the form of the parameter t, that means I'm integrating, let's say, time from 0 to 1, if we assume t, the parameter t is time. Okay, and at this point, this becomes a fairly simple problem, because what I really have here is the integral from 0 to 1, and I've got 1 plus 4t cubed multiplied by the square root of 5 dt. And you can see you could just factor the square root of 5 out. You can use the power rule here. This is really simple to solve. We'd get 2 root 5. Okay, so when we start thinking about these, a lot of times if you're thinking about these from a work perspective, that's where we're gonna head towards. So when we do it from a work perspective, we have like a force times a distance. That's what we're gonna get to when we're gonna start talking about integrating over vector fields a little bit later on. So for now, let's just kind of learn the mechanics of this. And then when we get into the applications, all of the different pieces of this are gonna make a little bit more sense. Okay, so part B here, same question. Notice that we've got a slightly different function, vector function r of t. We've got 1 minus t, 2 minus 2t, but we're still using the parameter 0 to 1. Now notice my graphs here. The first one, I was essentially using a vector that started at the origin, went to the point 1, 2. On the second problem here, I've got a vector function that's starting at the point 1, 2, and it's finishing at the origin. So we're essentially going in the opposite direction along the same path. Okay, so let's talk about here how we would set this up. So obviously we need to know r prime of t again, because we need our dx dt and our dy dt. These are a little bit different because we're going in the opposite direction. We get -1, -2. And then for my integral setup here, I'm integrating along the same curve in the opposite direction, 1 plus xy squared ds. And when I convert that over, I'm going to have an integral that goes from 0 to 1. And I've got my conversion here would be 1 plus x is now 1 minus t. Y squared would be 2 minus 2t squared. All of that multiplied by the length of dx dt squared plus dy dt squared, square root of 5, or the length of the derivative vector, and then multiply by dt. Okay, so there's a little bit of algebra here. You'd expand it out, do a little bit of work, but in the end, what you'll find is you actually get the exact same result. We get 2 root 5 again. So what that means is when we are integrating along a curve, we can, and when we're integrating with respect to arc length, we can change the direction of the curve and not change the value of the integral. So again, when we get to an application, this makes a little bit more sense. But essentially what we did was we kind of flipped the curve around, if you notice there. So when I'm thinking about my ds, it doesn't really matter which direction I'm going in. And remember, since we flipped the curve around, we essentially flipped our 0 to 1 instead of going along the curve from 0 to 1, from t is 0 to t is 1 in that positive direction. Now t is 0 to t is 1 went sort of in that negative direction. but it didn't make a difference in the end from the results because I'm integrating with respect to a change along the length of the curve. Okay, so we'll talk about why that matters in a little bit later on when we start thinking about line integrals with respect to x, y, and z. Okay, so here's another one that I want you to try. It says evaluate this line integral along the curve C, 2 plus x squared y, where C is the upper half of the unit circle, x squared plus y squared is equal to 1. Now, before you get too far into this, just remember you're going to have to come up with your parametric equations here. So since we're starting at the point 1, 0, I'm going to say my x is cosine t. I'm going to say my y is sine t. And I'm doing the top half of this circle. So I know my t constraints, t is going to be between 0 and pi. Okay, so what I want you to do is pause the video, set this up, and solve it out. You should find that this is a fairly simple process. Okay, so here's what you should have ended up with as a solution. We've got our, first of all, our line integral written out with everything written in terms of t. So that's what I did first, is I just substituted in 2 plus x squared y became 2 plus cosine squared t sine t. And then my ds this time is square root of sine squared plus cosine squared. Well, we know sine squared plus cosine squared is 1. So it's a square root of 1, which is just 1. So this actually simplified down really nicely. You do have to do a little bit of substitution with that part of the integrand in the end. But you end up with 2 pi plus 2/3. Not really anything that's too difficult to do. Now, again, when we're looking at these and we're not really talking about applications, it's more just the mechanics of the problem that I want you to focus on. And then when we get into the applications, what we're getting as a result is going to start having a lot more meaning, whether we get a positive number or a negative number, the direction that we go, whether we integrate with respect to arc length or x, y, and z. All of those things come into play when we start getting into the problem-solving applications. All right, so let's move on here, and I've got another application for you. So what this one says is find the area of the surface extending upward from the circle x squared plus y squared is equal to 1 in the xy plane to the parabolic cylinder z is equal to 1 minus x squared. Okay, so we want to find essentially what that area is with that domain, right? So we want to be thinking about the surface 1 minus x squared, and okay, so let's take a look at this next problem. It says find the area of the surface extending upward from the circle x squared plus y squared is equal to 1 in the xy plane to the parabolic cylinder z equals 1 minus x squared. So we have a circle in the xy plane, and essentially what you're doing is thinking of that circle extending upward, sort of in a cylindrical shape. And where does it intersect with the parabolic cylinder z equals 1 minus x squared? And that intersection is what's creating the surface that we're trying to find the area of. Okay, so essentially what we're doing here is we're going to integrate over this surface. And in a sense, you can think of this as a line integral along this curve. Okay, so let's talk about how we would set this up. So for my area just in general is going to look like this. I'm integrating along this curve, 1 minus x squared. Remember, it was z equals 1 minus x squared. And then we're going to use our arc length representation of this line integral. So since we're dealing with a circle, I'm going to use the same thing we just did. X is cosine t, y is sine t. Obviously, you could switch those around and it wouldn't make a difference. And this time we're going to go from 0 to 2 pi. Okay, so when we set this up now, we've got to be thinking about what we're using as our reference here for the arc length piece of this, and also for the curve or the line from the line integral perspective that we're integrating over. Okay, so the curve that I'm thinking about is the circle, right? The x squared plus y squared is equal to 1. And what I'm going to do here is I'm going to change this over into its parametric form. Okay, so let me rewrite this. I know I'm going to integrate from 0 to 2 pi. 1 minus x squared becomes 1 minus cosine squared. So 1 minus cosine squared t. And then for my arc length piece of this, it's just sine squared t plus cosine squared t dt. Okay, so in the end, when I solve this out, what I'm going to end up with here is my area being equal to the integral from 0 to 2 pi. Obviously, what's inside the square root there, again, is a 1. So we have sine squared t dt. And then when we integrate that all out, we can end up with pi. So getting an exact solution there, you'd have to use a trig identity to solve it out, but you could definitely get an exact solution for that. I don't want you to focus too much on all of the integration pieces of this as much as you focus on the setup for the problems. Okay, so from the perspective of thinking about what this all means, keep in mind we're integrating along this curve that we see here, right? So we're integrating along this curve as we go around this thing. I know that's kind of weird with the way I drew it, but the idea is, remember, the ds is a small piece of that length of curve. And then essentially what we're doing is we're adding up a bunch of areas as we go through there. So in 2D, right, we were adding up a bunch of rectangles. Now we're adding up all of the area of the surface as we go around that curve. So it's a little bit different way of interpreting it, but in the end, we end up with an area, just like we end up with an area when we're dealing with rectangles in a 2D space. When we start integrating along these curves, what we're doing is we're ending up with an area typically on a surface. Okay, so let's talk about doing line integrals with respect to x, y, and z. So before we were talking about integrating with respect to arc length. Here we're going to talk about integrating with respect to a specific variable. So this changes a little bit from what we were doing before when we were working in terms of rectangular approximation type of thought with integration, right? When we integrate along the x-axis or the y-axis or the z-axis, the change here is the fact that we're integrating along a curve. So when we think about our delta x, it has a slightly different meaning when we're trying to find that distance along the curve. So that's the big thing that we have to change about this. So here's our general setup, but what's really going to help us more than just seeing the delta x is going to be thinking about, okay, how do we represent that delta x when we have a multivariable situation? So what we have to think about is the fact that our delta x is actually going to be a little different this time. The way we're going to evaluate the delta x is by looking at the derivative of our x expression times our change in t. So the change in the parameter, and that would tell us how far we've moved in the x direction. So if you want to think of this from the perspective of differentials, this would be like dx dt times dt. and then these dt's end up canceling out, you're just left with dx. So all we're doing is we're writing that in a slightly different form so we can do this in terms of the parameter. Okay, so, and again, we can also do the same thing with respect to y. You can see that we've got our y prime t dt. So again, we're getting that change in y, but we're getting it now with respect to the parameter t because we're moving along that curve. Okay, so let's take a look at a couple of examples here. So it says evaluate this integral along the curve C, 3xy, where C is the line segment joining the points 0, 0, and 1, 2 with this given orientation. Okay, so notice that we're going to have a line integral with respect to y here because we see a dy. Okay, and it says that we are now going to go from the point 0, 0 to the point 1, 2. Okay, so a lot of this is similar, right? We need to get the parametric forms for x and for y, and we also need to have what we're going to do with our t's. What's our constraint for the t? Well, pretty straightforward here. My x of t is just going to be t. My y of t is going to be 2t because I'm moving twice as far with the same change. And my t values are just going to go from 0 to 1. Now, sometimes you can come up with different parametric forms of your curve. As long as the t values make it match up with the other form, everything will work out the same. So you may not have the exact same setup every time, but your end result should be the same because all of those things will sort of work themselves out. So what we're doing here is we're integrating along this curve C, 3xy dy. Now let's convert this over. So this is the same as integrating using the parameter t from 0 to 1. So for the x, we have t. For the y, we have 2t. And now remember, for the dy, we need to get dy dt times dt. So the derivative of our y here would just be 2. So that's going to be times 2 times dt. Okay, so fairly easy to solve from here. You end up with a value of 4. Okay, so again, if I were thinking about what's happening here, I'm integrating in the y direction this time. So the direction is going to matter. And that's what I want to show you here is that there is a difference this time. Look at part B. It says this time we're going to orient from 1, 2 to 0, 0. So we're going the opposite direction along the curve this time. So remember when we were doing this from an arc length perspective, we were just thinking about the distance we were moving along the curve. Well, now we're thinking about a dy, right? So on part A here, the first part of this problem, I'm moving in the positive y direction. Well, look at the second part of this problem. Now we're moving in the negative y direction. So I'm actually going to expect a different result this time because the direction matters. Okay, so what I mean by that is, let's start with setting up our curves here. So I'm going to say x is 1 minus t. I'm going to say y is 2 minus 2t. And my t values are going to go from 0 to 1. Now, you could also use the previous problem and just kind of reverse it in terms of the t values. But what I wanted to do is set up a parameter or a set of parametric equations where my initial t value gave me the point that I was looking for. Okay, so we're going to integrate along this curve C, and we've got 3xy dy. So again, convert this over. So we're going to integrate from 0 to 1. X is now 1 minus t. Y is 2 minus 2t. And then for our partial with respect to y, or our dy dt, we're just going to have negative 2 times dt. Okay, so now when we set this up, what we're going to be looking at here is just an integral in the end that's negative 12 times 1 minus t squared dt. And then from there, you can expand it out. You can solve it out. But what you'll find here is that you actually get negative 4 instead of positive 4. So the big thing that I want you to note there is that the order matters, right? So the direction that I'm going makes a difference. So the first one I was moving in the positive Y direction. The second one I was moving in the negative Y direction. So the order, or the direction I moved along the curve made a difference in my end result. All right, so we can also do these same ideas in 3 dimensions. And it's very easy to convert over to 3 dimensions. So the first one here is, let's say we were going to work in space in terms of arc length. So pretty straightforward. We know how to do arc length in 3 dimensions. So the only thing that really changes about our setup is the fact that our arc length is now the square root of dx dt squared plus dy dt squared plus dz dt squared. Okay, so when we solve these kind of problems out, it's very easy to do. So everything's pretty much the same. So this one, it says, evaluate the line integral along this curve C, xy plus z cubed ds from the point 1, 0, 0 to the point -1, 0 pi along the helix C that is represented by these parametric equations. Okay, so remember a helix sort of has that sort of spiral shape, but we're moving in a circular pattern, either up or down. So that's what we're looking at here. So what I want you to do is just pause the video, take a couple of minutes and solve this out. When you come back, I'll show you the solution. Okay, so here's what you should have come up with for this. You can see that the first thing I did was convert everything in terms of t. My arc length, my ds, became square root of sine squared plus cosine squared plus 1, which simplifies down really nicely to the square root of 2. And then the rest of this integral is fairly straightforward to solve. There's a little substitution that goes on in there, but pretty easy to solve it out and get an exact solution. So we end up with square root of 2 pi to the 4th over 4. Okay, so again, not really difficult to do, but you're also sort of thinking about the surface area along, or I guess on the surface of xy plus z cubed as you follow along that path. Okay, so think about that from the perspective of what is this actually representing. All right, so last thing we're going to talk about here are line integrals of vector fields. And when we talk about this is really, we're going to start to get into some of the applications that we're going to have for line integrals. The primary application we're going to look at is work. Remember, when we did work as force times distance. But when we thought about it from a vector perspective, where we had, force in more than one direction, we would write our force function as a vector function. And then if we did a dot product of that with our distance, then that would give us the end result of our work. Okay, so remember, depending on how we were moving, that displacement vector would then have an I component, a J component, a K component, maybe all 3. But anyway, you do the force dotted with the displacement vector, and that would give us the work. So we want to keep that concept in mind as we look at this. And now what changes here is we're going to start integrating over a vector field. So we're going to have these forces that are going to be varying, and the vector is going to be varying as we move through the vector field along some path. Okay, so the way that we do this is we have to take the direction that we're moving into account by taking the tangent of the curve, because that's going to give us the direction that we're moving at any particular point along that curve. So remember, we found the unit tangent by taking the derivative of the displacement vector. And then from there, we would go through and we would turn that into a unit vector. So now what we want to do is just use that and multiply by ds, because that would be the distance that we moved. And that would take into account the direction that we moved by using the unit tangent. And then from there, when we dot product that with the force, that's going to give us the work. Okay, so slightly different setup, but it's still the same general concept. Okay, so the big idea here is, instead of breaking this into like a delta x and a delta y and a delta z, we're breaking this into a delta s. So we're using a bunch of small pieces of arc length. And for the direction that we're moving for that little piece of arc length, that's where we're using the unit tangent vector. Okay, so here's the setup that we're going to use in the end. But in the end, it's still force times distance, or force dotted with distance, if you want to think of it that way. But here's my force, and then here's my displacement for that particular force along that small piece of the path. And then we're going to add up all those pieces. Okay, so let's take a look at just one example here. It says, find the work done by the force field F on a particle that moves along the curve C. So we have this function xyi plus x squared j, and our curve is x is equal to y squared. So we're moving along a parabolic path. Okay, so the setup here is fairly straightforward. We know that from the path perspective, I've got to set up parametric situation, and I'm saying x is t squared and y is equal to t, and using that I know that my t is going to be bounded between 0 and 1, and I also have the fact that now I can use this displacement vector essentially to be t squared t, and the derivative of that, which is going to give me the direction, would be 2t1. Okay, so if I want to think of my force function in terms of t, I can just do a substitution here into my force function. Remember, the force function was xyi plus x squared j, so I'm going to substitute in for xy. When I plug in xy, that's going to give me this new vector, which is essentially going to be t cubed, because that's my x, which was t squared times t. And then for the j component, I had x squared. Well, x squared is the same as t squared squared. That gives me t to the fourth. And then from there, we just have to go through and we have to integrate now. So we just have to remember what the setup is for this. We're integrating along this curve C. And we're going to do the dot product of our force and then some small piece of this direction, or this arc length, I should say. Okay, so when we integrate this, we're going to go ahead and set up our dot product here. You can do this outside of the integral if you want, but essentially what I'm doing here is I'm doing the dot product of t cubed t to the fourth dotted with 2t1. And from there, okay, and then from there, this becomes a really simple problem. So all I have to do now is get the result of that dot product, which ends up being 3t to the fourth. And I end up with 3/5. So we have looked at situations like this where we had varying forces before, but when we had a varying force before, we were always thinking about just moving in the x direction or moving in the y direction, and sort of working with those even from a multivariable perspective was fairly simple. But now that we're working where the force is varying as we move along the path, now we have to do this in a slightly more advanced way and take these line integrals into account.